In this video, we're just going to practice some more antiderivatives. Alright, so now we know pretty much all of our major antiderivative rules we need. We have the reverse power rule. We can go backwards from our trig functions, go backwards from exponentials, and now we can hit that one weird thing that we couldn't do before. 1 over x turns into the natural log again. Generally, there'll be absolute values there. We also have substitution as a way to simplify our antiderivatives so that we can get them to look like one of these and then do the antiderivative. So the antiderivative part is the really hard part. We need it to look pretty simple to do an antiderivative, so we use u substitution to simplify first before we do that. All the examples in this video you can technically do now because you have all the rules. I can understand, maybe you can't do them all just by looking at them yet. We're going to practice, but for all these ones, I'm just going to go ahead and do them. But when you first see the problem, just pause it, see if you can figure out what the process would be before I go through it. This one, e to the x square root of 1 plus e to the x. Right away, when I look at this one, I see that 1 plus e to the x, its derivative is right there. So right away, I know this should be u equals 1 plus e to the x. Whenever you're looking at a problem, if you see an expression's derivative somewhere else in the problem, that's your hint. Just make it u. It's going to simplify because those things will cancel out. So du is going to be e to the x dx, dividing. I get that. So now my equation, oops, that's not u. E to the x square root of u times du over e to the x. Again, I know I did this, I picked a good u, and sometimes you try a u and it doesn't work, but here I picked a good u because the things with the x's cancel out. Right. So now my problem looks a lot simpler. I just have a square root, and now you might say, like, well, how the heck do I take the antiderivative of square root? Remember, square roots, we did this a lot earlier in the year. You can always rewrite as the 1/2 power. Then I do my reverse power rule. Add 1 to the exponent, so 1/2 plus 1 is 3/2. Divide by the new exponent. And then plug back in your u for your final answer. And then you're done. You might see for a multiple choice question, this might be written something like this. And that's just if you kind of separate the 1/2 part of your fraction exponent back into a square root, and the 3 would stay. So you might see it like that, but of course, if this was a test or something, I'd be fine with this answer. Integral of tangent of x. If you can figure this one out on your own without my help, then you're in an amazing place. How the heck can you do the integral of tangent? You might be looking through your notes and looking at your trig derivatives, but we don't have an antiderivative just for tangent. We have one for tangent times secant. Tangent times secant goes backwards to secant, but tangent all by itself we don't have an antiderivative for. So what are we supposed to do here? We don't really have anything to work with. Well, if you're ever looking at a trig expression, you don't know where to start. One way you can always start is by just rewriting it using our alternative definitions for our trig functions. So instead of writing tangent, I can write, apparently I can't write, tangent is sine divided by cosine. And then you look at this and say, okay, well, that doesn't help me. I still have this fraction, sine and cosine. What can I do? Well, sine and cosine are their own derivatives. So if I make one of these u, it's going to cancel out with the other one. But one is the right way to go, one's not. If I make u sine, I'm going to get two things in the denominator. It's going to cancel out. So I actually want to make u cosine of x. du is going to be negative sine of x dx, and a divide. Let's get this. So now my equation is going to look like this. Sine I haven't done anything with. Cosine I called u. And then dx is du over negative sine of x. Again, I know I picked a good u eventually because the stuff with the x's goes away. The negative sign's still going to hang out, so that negative sign I'll just write at the front. I have a 1 on the top and u on the bottom, and a du. And now, because I made u the bottom here, this piece, 1 over u, it just turns into the natural log. And I go backwards and remember that u was cosine of x. And again, I use absolute values for these answers because you can only plug in positive values into the natural log. So it just makes it more correct. This tangent looks pretty simple to take its antiderivative, but it doesn't have a nice trig antiderivative. It actually looks pretty nasty. But that's our antiderivative of tangent. All right, this one is not obvious at all. It's not one that I expect you to memorize. All right, it's a chance they could ask it on the AP exam. I always know that this is not a simple trig answer. You have to do this kind of process to get this answer. X over the square root of 1 plus x squared. When you see this one, I hope one of the things you do think about is our trig antiderivative, or trig inverse antiderivatives. So we had something like arcsecant is 1 over x times square root of x minus 1. Arctangent is 1 over 1 plus x squared. Arcsine is 1 over square root of 1 minus x squared. All right, so we had things that looked like this when we did our inverse trig derivatives. All right, but the difference between these and this problem is the x on the top. If this was the 1 on the top, this would be really similar to this one. All right, but it's not a 1 on the top or a number on the top, so it's not an inverse trig derivative. So the only other thing I can think of here is to make u 1 plus x squared. Why is that my first idea? Because I know the derivative of x squared is 2x, so it should end up canceling with that. All right, so I'm always looking for the things that I can make u so that its derivative is somewhere else in the problem. And so I make my u, take derivatives of that, rewrite my equation. And again, I know I picked a good u because the x's cancel out. Sometimes you get these extra coefficients, so this 2 on the bottom is just going to hang out. Just make sure it's 1/2 and not 2 because it's on the bottom of the fraction. And here you might be thinking, okay, this is going to give me something with a natural log, but the natural log is only just 1 over x or 1 over u. Here it's the square root of u. So just like with our other square root problem, I can rewrite this as u to the negative 1/2 because it's on the bottom. Then I can do my reverse power rule, add 1 to the exponent, divide by the new exponent. This 1/2 and that 1/2 cancel. And I get 1 plus x squared to the 1/2 plus c is my final answer. I think if this was on a multiple choice question, they would put this 1/2 back to a square root. I think you'd probably see it like this. All right, so again, antiderivatives are much harder than derivatives. I understand that. You're just kind of like thinking about things. All right, I think when I look at this one, I was like, oh, this might be an inverse trig antiderivative, but this x at the top kind of told me it wasn't because it was just have a number on the top. So it's the only other thing I can do. Try to do u substitution. Use the thing inside of something else. So I'm going to, of course, pick the thing inside the square root. E to the 1 over x squared. If I make u x squared, it creates a 2x, so it doesn't really help here. So my idea here is to make u, again, the thing inside of something else. I just quickly realized that making it the bottom of the denominator is not right, even though we've done that a lot. The thing inside of something else, 1 over x is inside of the exponential, so I'm going to make u 1 over x du. It's going to be negative 1 over x squared dx. So negative x squared du equals dx. All right, if you don't understand this part, all right, this is x to the negative 1. The power rule, negative 1, x to the negative 2. Rewriting x to the negative 2 with a positive exponent. This is now the integral of e to the u for x squared times negative x squared du. Again, sometimes you pick u and it doesn't work. I'm picking the right u because I've done this a lot. But you know you've done it right because x squared cancels out. You should always be happy when you see an antiderivative of e to the u because you just get back the same thing. And I plug back in my u. And I'm done. So again, one way you can always go is just like experiment with u's. Right? We could try to make u x squared. You see that doesn't cancel out with anything. You could try to make u e to the 1 over x. And you see that makes things way more complicated. And then, of course, u is actually the thing that's inside of something else, so it's just 1 over x. Here's another example. All right, so here's a lot of things that are going on. There's an x squared, there's a cosine squared of x cubed, there's a sine of x cubed. Right away, I think I know what u is going to be. I didn't practice this problem before the video, but I think u is going to be cosine of x cubed. And why is that? Because cosine squared of x cubed is actually just cosine of x cubed squared. So even though it's kind of hidden in the notation, cosine of x cubed is actually inside of something else. So let's just see what happens if I make u cosine of x cubed du. Do the chain rule. Cosine turns into negative sine. X cubed turns into 3x squared. All right, so what is my equation going to turn into now? I haven't done anything with x squared. I made u this, so this is going to be u squared sine of x cubed. Still looks pretty complicated. Du over negative sine x cubed times 3x squared. Right? Sine of x cubed cancels out. X squared cancels out. And all that's left behind is that negative 3. So it's going to be negative 1/3. I don't know why I switched to blue. Negative 1/3 integral of u squared du. Now I do my reverse power rule. The negative 1/3 stays. U squared becomes u cubed over 3. Add 1 divided by the new exponent. It's going to be negative 1/9 cosine cubed of x cubed. All right, so again, just thinking about what would make sense for u to be. Generally, u is going to be something inside of something else. And here, that cosine of x cubed is inside of the squared. You might also think, well, I'm just going to make u x cubed. And that would work. You'd actually have to do a second substitution after you simplify that one. So making u cosine of x cubed, you get it done in one step. But you could, if you were able to keep up with all your notation and everything, do a substitution of x cubed, and then you would end up doing like a substitution of cosine of u. That's also possible. All right, so a lot of practice in there. Hopefully you understood some of them. Hopefully some, like the tangent one, you might not have got the first time, but hopefully you kind of understand where the things we're looking for. You have to know your basic integrals to do any of these problems, so make sure you know the things. And then most of the time, if it looks complicated, you're going to do substitution. The only time I would say you're not doing substitution if it looks complicated is if you had something like this. That looks really complicated, but this is one of our inverse trig antiderivatives. So those are the ones that you had to remember separately because they look complicated, but they're actually not super complicated in terms of the steps you have to do. Complicated in terms of the formulas you have to memorize. There's not a lot of steps that go into it though. All right, so make sure you know those basic things. Make sure you're working on your flashcards, you have all this stuff memorized, and you're practicing your u substitution.